How old is the universe? It's one of the biggest questions you can ask. The simple answer is about 13.8 billion years. But that number feels almost meaningless. It's too big to really grasp. The interesting part isn't the number itself. It's how we figured it out. How do we know? It's a detective story, pieced together over a century by thousands of people, using clues written in the light from distant galaxies. It's a story of cleverness, mistakes, arguments, and incredible precision. The story starts with a simple observation. The universe is getting bigger. In the 1920s, an astronomer named Edwin Hubble spent his nights at the Mount Wilson Observatory in California, staring at faint smudges of light. At the time, many people thought these smudges, called nebulae, were just gas clouds inside our own Milky Way galaxy. But Hubble had a powerful new telescope. He was able to see individual stars within some of these smudges. He found a special kind of star called a Cepheid variable. These stars have a weird and useful quirk. They pulse. They get brighter, then dimmer, then brighter again, on a very regular schedule. And a decade earlier, an astronomer named Henrietta Leavitt had discovered the secret of these stars. She found a direct link between how fast a Cepheid pulses and how bright it truly is. A slow pulse means a very bright star. A fast pulse means a dimmer star. This was a breakthrough. It gave astronomers a cosmic yardstick. Think about it like this. Imagine you see two identical 100-watt light bulbs. One looks bright, and one looks dim. You know instantly that the dim one is farther away. You can figure out the distance just by comparing how bright it looks to how bright you know it really is. Henrietta Leavitt gave us a way to know the true wattage of these cosmic light bulbs. By measuring a Cepheid's pulse, we know its intrinsic brightness. Then we measure how bright it appears in our telescope. The difference tells us the distance. Hubble used this trick to measure the distance to the Andromeda Nebula. He found it was millions of light years away. It was far, far outside our own Milky Way. That faint smudge wasn't a gas cloud. It was an entire galaxy, just like our own, filled with billions of stars. This single discovery changed everything. The universe was suddenly vastly bigger than we had ever imagined. But Hubble didn't stop there. He also measured the light from these distant galaxies. And he noticed something else. The light was stretched. This is called redshift. You know, it's like the sound of a siren. When an ambulance is coming toward you, the sound waves are compressed and the pitch is high. As it passes you and moves away, the sound waves are stretched out and the pitch drops. The same thing happens with light. If a galaxy is moving away from us, the light waves it emits get stretched. This stretching shifts the light toward the red end of the spectrum, hence redshift. Hubble measured the redshift for many galaxies. And because redshift tells you speed, he now had two key pieces of information for each galaxy, its distance from us, and the speed at which it was moving away. When he plotted these two things on a graph, he saw a straight line. The farther a galaxy was, the faster it was moving away from us. This relationship, now called Hubble's law, was the first real evidence that the universe is expanding. This is a crucial point. It doesn't mean we're at the center of some great explosion. Imagine baking a loaf of raisin bread. As the dough rises, every raisin moves away from every other raisin. A raisin in the middle sees all the others moving away. A raisin near the edge sees all the others moving away too. From any raisin's perspective, everything is expanding away from it. That's our universe. Every galaxy is moving away from every other galaxy. This discovery of an expanding universe gave us the key to its age. If the universe is expanding, then in the past it must have been smaller. And if you go back far enough, everything must have been packed together in one incredibly dense hot point. The moment it all started expanding is what we call the Big Bang. So the age of the universe is simply the time it has taken for everything to expand to its current size. We can calculate this. If we know how fast things are expanding now, we can rewind the clock. The rate of expansion is a number called the Hubble Constant. Figuring out the age of the universe became a quest to measure this one number as accurately as possible. The equation is simple in concept. The age is roughly 1 divided by the Hubble Constant. A faster expansion rate, a larger Hubble Constant, means the universe reached its current size more quickly. That would mean it's younger. A slower expansion rate, a smaller Hubble Constant, means it took longer to get where it is today. That would mean it's older. For decades, the biggest challenge in cosmology was measuring the Hubble Constant. It was incredibly difficult. To get the constant, you need to measure a galaxy's speed and its distance. Speed was the easy part. Redshift gives you that pretty accurately, but distance was the killer. Measuring distances across millions of light years is a monumental task. Astronomers built something called the cosmic distance ladder. It's a series of steps, each one relying on the one before it, to measure farther and farther out into space. The first rung is the most direct method we have. It's called parallax. Hold your thumb out in front of your face and close one eye. Now switch eyes. Your thumb seems to jump back and forth against the background. That's parallax. Your two eyes give you two different perspectives. Astronomers do the same thing, but with a much bigger baseline. Instead of the distance between your eyes, they use the distance of Earth's orbit around the sun. They take a picture of a nearby star in January, then they wait 6 months and take another picture in July when Earth is on the opposite side of the sun. The star will appear to have shifted slightly against the background of much more distant stars. By measuring that tiny shift and knowing the size of Earth's orbit, they can calculate the distance to the star using simple trigonometry. This method is the gold standard. It's pure geometry, but it only works for relatively close stars inside our own galaxy. Beyond that, the shift is too small to measure. That's where the next rung comes in the Cepheid variable stars that Hubble used. We find Cepheids in our own galaxy that are close enough to have their distance measured by parallax. This calibrates them. It lets us confirm, with a known distance, that the period-luminosity relationship discovered by Henrietta Leavitt really works. Once we're sure of that, we can look for Cepheids in other, more distant galaxies. We measure their pulse, determine their true brightness, and then calculate their distance. This gets us out to neighboring galaxies, maybe 50 or 100 million light years away. But to measure the Hubble constant accurately, we need to go even farther. We need another brighter standard candle. The best one we have is a specific kind of exploding star, a type Ia supernova. These supernovae are astonishingly bright. A single one can briefly outshine its entire host galaxy. They can be seen clear across the universe. And most importantly, they are remarkably consistent. A type Ia supernova happens when a small dense dead star called a white dwarf, part of a binary star system, sucks material off its companion star. When the white dwarf's mass hits a very specific limit, about 1.4 times the mass of our sun, it becomes unstable and detonates in a thermonuclear explosion. Because they all explode at the same mass, they all reach roughly the same peak brightness. They are fantastic standard candles. So, the strategy is to find a galaxy that's close enough for us to see both Cepheid variables and has also had a type Ia supernova. We use the Cepheids to get a precise distance to that galaxy. That, in turn, tells us the true brightness of the supernova. Once we have that calibrated, we can look for other type Ia supernovae in galaxies billions of light years away. By measuring how bright they appear, we can calculate their distance. This allows us to build a Hubble diagram, plotting distance versus speed for galaxies across the entire observable universe. For a long time, this was the main way we tried to pin down the age, but it was messy. Different teams got different answers. In the mid-20th century, the measurements of the Hubble constant were so high that they implied the universe was only a few billion years old. This created a huge problem, what astronomers called the age crisis. Geologists already knew that Earth was billions of years old. And astronomers knew from studying stars that some star clusters were at least 10 or 12 billion years old. You can't have stars that are older than the universe they live in. It was a clear contradiction. This told scientists that something was wrong with their measurements. They went back and re-examined their assumptions. They discovered there wasn't just one type of Cepheid variable, there were two, and they had been mixing them up. They refined their techniques. The estimated age of the universe started to get older, slowly creeping up toward a more comfortable number. But this method, relying on a ladder of measurements, still had a lot of potential for error. Each step in the ladder adds a new layer of uncertainty. What if our parallax measurements are a little off? That error gets carried up to the Cepheid distance calculations. Any error in the Cepheid calculations then gets passed up to the supernova measurements. Scientists wanted another way to find the age, a completely independent method that didn't rely on the Hubble constant at all. The second approach was much more direct, just find the oldest thing in the universe and measure its age. If you can do that, you know the universe has to be at least that old. It gives you a minimum age, a floor. The most obvious candidates were the oldest stars, but how do you tell a star's age? You can't just look at it. The key is to look at large groups of stars that were all born at the same time. The best places to do this are ancient structures called globular clusters. These are dense spherical swarms of hundreds of thousands of stars, all tightly bound by gravity. They orbit our galaxy and are among the oldest objects in it. Crucially, all the stars in a globular cluster formed from the same cloud of gas at the same time. They are a perfect laboratory for studying stellar aging. A star's lifespan is determined almost entirely by its mass. A massive star is like a gas-guzzling SUV. It has a lot of fuel, but it burns through it incredibly fast, living for only a few million years before exploding. A low-mass star, like our Sun or smaller, is like a fuel-efficient compact car. It sips its hydrogen fuel slowly and can live for billions or even trillions of years. So, when a globular cluster is born, it's filled with stars of all masses. It has bright, massive blue stars and dimmer, low-mass red stars. As the cluster ages, the most massive stars die first. After a billion years, all the stars more than a few times the mass of the Sun are gone. After 10 billion years, even stars like our Sun are starting to die out. Astronomers can take a snapshot of a globular cluster and plot its stars on a diagram of temperature versus brightness. For a young cluster, you see a full range of stars. For an old cluster, you see that the most massive, brightest stars are missing. They've already evolved off the main sequence of their lives and turned into red giants. The point on the diagram where stars are just now starting to peel away and die is called the main sequence turnoff point. By finding this turnoff point and using our well-tested models of how stars work, we can calculate the age of the cluster. It's like walking into a room full of candles of all different sizes that were all lit at the same time. By seeing which candles have just burned out, you can figure out how long ago they were all lit. When astronomers did this for the oldest globular clusters, they consistently got ages of around 12 to 13 billion years. This was a fantastic result. It resolved the old age crisis. The universe was at least 13 billion years old, which was comfortably older than the 10 billion years or so that the Hubble Constant measurements were suggesting at the time. This gave scientists confidence that they were on the right track. Another independent method was to look at the cooling of white dwarfs. As we said, these are the dead, burnt-out cores of stars like our Sun. They don't generate any new energy. They are just glowing embers slowly cooling and fading over cosmic time. By searching for the very faintest, coolest white dwarfs, we can get an estimate of how long they've been cooling. The oldest ones also point to an age for our galaxy's disk of around 12 or 13 billion years. So, by the late 1990s, we had two different approaches. One, for measuring the expansion of the universe, was giving an age somewhere between 10 and 15 billion years. The other, from measuring the age of the oldest stars, was giving a firm lower limit of about 13 billion years. The numbers were getting closer, they were consistent, but the precision still wasn't great. The big breakthrough, the measurement that would give us our current hyper-precise answer, came from looking back at the very beginning of time itself. It came from studying the afterglow of the Big Bang. This afterglow is called the Cosmic Microwave Background, or CMB. It's the oldest light in the universe. In the first few 100,000 years after the Big Bang, the universe was an incredibly hot, dense soup of particles and radiation. It was so hot that atoms couldn't form. Electrons were stripped from protons, creating a plasma. Light particles, photons, were constantly bouncing off these free electrons, trapped in a cosmic fog. The universe was opaque. But as the universe expanded, it cooled. Eventually, after about 380,000 years, it cooled enough for protons and electrons to combine and form the first neutral hydrogen atoms. Suddenly, the photons were free. The fog cleared, the light was released, and has been traveling through the universe ever since for over 13 billion years. As the universe has expanded, this ancient light has been stretched, just like the light from distant galaxies. Its wavelength has been stretched all the way from visible light down to the microwave part of the spectrum. Today, this radiation fills all of space. It's a faint microwave hiss coming from every direction in the sky. It was first detected by accident in the 1960s by two radio astronomers, Arno Penzias and Robert Wilson, who were trying to get rid of some persistent noise in their radio antenna. They even cleaned out pigeon droppings, thinking that was the cause. The noise wouldn't go away. It turned out they had stumbled upon the echo of creation. The CMB is a baby picture of the universe. It's a snapshot of what the universe looked like just 380,000 years after it began. And it holds the ultimate key to its age. At first glance, the CMB is incredibly uniform. The temperature is almost exactly the same in every direction you look, but it's not perfectly uniform. There are tiny, minuscule fluctuations in temperature, differences of just 1 part in 100,000. These tiny hot and cold spots were first mapped in detail by a NASA satellite called COBE in the early 1990s, and then with much higher precision by satellites named MOP, and most recently, the European Space Agency's Planck satellite. These tiny fluctuations are hugely important. They were the seeds of all structure in the universe today. The slightly denser, slightly cooler spots had a little more gravity. Over billions of years, they attracted more matter, eventually growing into the galaxies and clusters of galaxies we see today. The slightly less dense, hotter spots became the great voids in between. And here is how this gives us the age. We now have an incredibly detailed model of the universe called the Lambda CDM model. It's our standard model of cosmology. It's basically a recipe for the universe. The recipe has a few key ingredients: regular matter, the stuff we're made of; dark matter, a mysterious substance that provides most of the gravity in galaxies; and dark energy lambda, a mysterious force that is causing the expansion of the universe to accelerate. Using this model, we can run a simulation on a supercomputer. We can start with a universe full of these ingredients right after the Big Bang and tell the computer how fast it should expand. We let the simulation run for 380,000 years. The physics of how the primordial plasma behaves is very well understood. The simulation will produce a predicted map of what the CMB's hot and cold spots should look like. It will tell us the typical size of these spots on the infant universe's sky. Then we compare that predicted map to the real map from the Planck satellite. Do they match? We can tweak the knobs on our simulation. We can change the amount of dark matter, the amount of dark energy, the amount of regular matter, and the expansion rate, the Hubble constant. We keep running simulations, tweaking the recipe until our simulated CMB map is a perfect match for the real one we observe. The recipe that produces the perfect match is our best description of the real universe. It's an incredibly powerful technique because the pattern of the CMB is sensitive to all of these different parameters at once. And one of the numbers that comes out of this perfect fit model is the age of the universe. The data from the Planck satellite, released in its final form in 2018, is so precise that it has constrained this model to an incredible degree. It has measured the ingredients and the expansion rate with stunning accuracy, and the age it gives us is 13.77 billion years, with an uncertainty of only about 21 million years. That's an accuracy of better than 0.2%. It is an astonishing scientific achievement. This number is consistent with the ages of the oldest stars. It's consistent with the expansion rate measured from the distance ladder. All the pieces of the puzzle fit together. Well, almost. Science is never quite that tidy. And right now, there's one nagging problem, a new tension that has emerged in cosmology. It's a bit like the old age crisis, but much more subtle. The two best methods for measuring the Hubble constant, the rate of the universe's expansion, are giving slightly different answers. On one side, you have the team using the CMB. The Planck satellite data, when fed into our standard cosmological model, gives a Hubble constant of about 67.4 kilometers per second per megaparsec. On the other side, you have teams that have continued to refine the cosmic distance ladder using the Hubble Space Telescope to measure Cepheids and supernovae. These teams, most notably a project called SHOES, get a value of about 73. This might not sound like a big difference, but the error bars on these two measurements are now so small that they don't overlap. It's not just a measurement error anymore. It seems to be a real discrepancy. Both teams have checked their work again and again. They've looked for any possible source of systematic error. So far, the disagreement remains. What could it mean? There are a few possibilities. One is that there's still some subtle unknown error in one of the measurement techniques. Maybe our understanding of Cepheid variable stars or Type Ia supernovae isn't as perfect as we think. Or maybe there's some quirk in the CMB data we've misinterpreted. That's the boring answer. The more exciting possibility is that our standard cosmological model, the Lambda CDM model, is incomplete. That model is what we use to get from the CMB data to the Hubble constant. If the model is slightly wrong, the number it spits out will be slightly wrong. Maybe there's some new physics happening in the early universe that we don't know about. Perhaps there was an extra type of particle, sometimes called dark radiation, that changed the expansion rate right after the Big Bang. Maybe dark energy isn't constant, but changes over time. Scientists are actively working on this. New telescopes, like the James Webb Space Telescope, are making even more precise measurements of the distance ladder. New CMB experiments are planned to scrutinize the early universe with even greater detail. This is how science works. It's not about having all the answers, it's about finding the inconsistencies, the little bits of grit in the gears, because that's where the new discoveries are made. So, when we say the universe is 13.8 billion years old, it's not a guess. It's a number born from an extraordinary chain of evidence. It comes from understanding the expansion of space itself. It's backed up by the ages of the most ancient stars we can find. And it's pinned down with incredible precision by the faint, leftover heat from the Big Bang. We are very, very confident in that number, but the story isn't over. The fact that there's still a tension, a small disagreement at the cutting edge of our measurements, tells us that there's still more to learn. The universe, it seems, still has a few secrets left to share.